Alright, so next we'll prove a theorem. Let the set F, together with some notion of addition and some notion of multiplication, be a field. Then the linear equation a times x plus b equals c, where a, b, and c are in the set F, and a is non-zero, has a unique solution, in the field F. Now notice the restriction on the element A, it is non-zero, otherwise the variable x vanishes and we have an equation only in the case that B and C are the same element. So proof, let y equal a times x, then as the set F under addition is a group, the equation y plus b equals c has a unique solution, in the group, namely y equals c plus the additive inverse of b. So now we need to consider two cases. So case 1, suppose that c plus the additive inverse of b is not 0. Then, as the non-zero elements of the set F under multiplication is a group, the equation a times x equals c plus the additive inverse of b has a unique solution, in the group consisting of the non-zero elements of the set F under multiplication, namely x is the multiplicative inverse of a times the sum of c and the additive inverse of b. So case 2, suppose that c plus the additive inverse of b is 0, then the equation a times x equals 0 has the unique solution, x is equal to 0 in either case. The equation ax plus b equals c has a unique solution in the field which consists of the entire set F under addition and multiplication. All right. All right, new definition. Once again, let the set F, together with some notion of addition and some notion of multiplication, be a field. The n-dimensional affine space over the field F is the set, which we denote F superscript n, and this is a set of ordered n tuples, C sub 1 through C sub n, where each element in the n tuple, C sub I, is in the set F, or is an element of the set F. So as the set of rational numbers, together with normal addition and normal multiplication, is a field, the set of rational numbers itself is a one-dimensional affine space. Now, in contrast, the set of integers is not an affine space. Now, we will have much more to say about affine spaces in later lectures, but for now we're going to return to magmas and define a new structure. A quasigroup or quasigroup is a magma, and so the set Q is closed under the operation star. So a quasigroup is a magma satisfying the following property. For every pair of elements, A and B, in the set Q, there exists unique elements, X and Y, also in the set Q, such that A star X is equal to B and Y star A is equal to B. So again, let's look at this definition. For every pair of elements, A and B, there is exactly one element X in the set such that A star X equals B, and there is exactly one element Y in the set such that Y star A is equal to B. Now, one description of a quasigroup is that it is a magma for which it is always possible to divide the elements and remain in the magma. So with this in mind, the element X is often denoted A backslash B, and the unique element Y is often denoted B forward slash A, where we have a distinct notion of division on the left and division on the right. This notation means that we are dividing B on the left by A, and this notation means that we are dividing B on the right by A. And so again, one description of a quasigroup is that it is a magma for which it is always possible to divide one element by another and remain in the magma. Another thing to notice is that by definition, every linear equation with coefficients in the quasigroup has a unique solution. Also in the quasigroup. So next we will show that left and right cancellation laws hold. So let the set Q together with some binary operation star be a quasigroup. Then the left and right cancellation laws hold. That is, if A star B is equal to A star C, then this implies that B is equal to C. And if B star A is equal to C star A, then this implies, once again, that B is equal to C. So proof. First statement, suppose that A star B is equal to A star C. Then as a quasigroup is a magma, it is closed under the operation star, and so A star B is the same element as A star C. So let's rename that element. So let A star B, which is the same as A star C, be the element D. Then, as A star B equals D, we have that B is the unique element. Such that A star B is equal to D. But as A star B is equal to A star C, we have that C is also the unique element. Such that A star C is equal to D. And so as that element is unique, we must have that B and C are the same element. So second statement, suppose that B star A is equal to C star A. Once again, we have closure of the set under the operation star, and so B star A is an element in the set, as is C star A, and as the two are equal, it is the same element, so we rename it. Let B star A equal C star A, and let's rename it the element D. Then the element B is the unique element. Such that B star A is equal to D. Now, as B star A is equal to C star A, we have that C is also the unique element. Such that C star A is equal to D. And so as the element is unique, we must have that B and C are the same element. Okay? So new definition. A loop is a quasigroup with identity, that is, there exists a unique element, which we'll denote E, in the set Q, such that for every element A in the set Q, we have that A star E is the same as E star A, which is the element A. So notice that in a loop, for every element A in the set Q, there exist unique elements X and Y in the set Q, such that A star X gives identity and Y star A gives identity. Now, we often say that this equation on the left means that there exists a unique right inverse for the element A, and that the equation on the right means that there exists a unique left inverse for the element A. Now, this is not the same as saying that the element A has a unique inverse in the set. In order for that to be true, the elements x and y must be the same element. Now, there are two ways in which this occurs. One is if the operation is commutative. So suppose that the operation star is commutative over the set Q. Then, as A star x is identity and Y star A is identity, we have that A star x is equal to Y star A. Now, if the operation is commutative, as we are assuming, then we can rewrite this equation as x star A is equal to Y star A. And as the right cancellation law holds, we have that x is equal to y. And so if the operation is commutative, for every element A in the set Q, there exists a unique element in the set Q such that A star x is the same as x star A, which is the identity. So if the operation is commutative, every element A has a unique inverse. So now suppose that the operation star is associative over the set Q. Then as a reminder, we have that A star x is identity and Y star A is identity. So we'll work with the equation on the left. We will perform the operation star on the left with the element y, so that we have y star, the quantity, A star x, is y star identity. Now, as we are assuming that the operation is associative, we can regroup the terms so that we have y star A star x is equal to y. Now, as y star A is identity, we have identity star x is equal to y, or simply x is equal to y. And so if the operation is associative, we have that for every element A in the set Q, there exists a unique element x in the set Q such that A star x is the same as x star A, which is the identity. And so if the operation is associative, every element in the set has a unique inverse. So we can now give an alternate definition of a group. A group is an associative loop. That is, the operation star is associative over the set Q. And so, given a magma, if the operation is associative, then we have a semigroup. Now, if the operation is not necessarily associative, but each linear equation has a unique solution, then we have a quasigroup. If in a semigroup there exists a unique identity element, then we have a monoid. And if in a quasigroup there exists a unique identity element, we have a loop. And if each element in the monoid has a unique inverse, then we have a group. And if the operation in the loop is associative, then we also have a group. And as we have demonstrated, if the operation is associative in a loop, then each element has a unique inverse. Okay, so we'll end here for today. Next time we'll look at some examples of quasigroups, and then we will continue our study of group theory in earnest. So I hope you have enjoyed the 11th lecture. Thanks for watching.